Thank you for that excellent introduction, Alex. I really appreciate it. I really appreciate being here. It's wonderful to participate with Quantum BC and to be the second talk in the series. It's a really good opportunity. So thank you. And I'm sorry that we can't all be in the same room. Hopefully I touch on things in this talk that are applicable to everyone. I think that there's a bit of physics in this. There's some chemistry. There's also some computer science. And for my engineering colleagues, I'm sorry I don't work on anything so fascinating, but there are some challenges to reach for in this talk that would really help the theory come to life in this talk. So today I want to talk about what we can do with quantum algorithms sort of in the here and now, and then what we can do in the future. And this is sort of the focus of my research group. So if you're interested in reaching out, then I know that there's a lot of opportunity to come to Victoria or go back to UBC or go to Simon Fraser, and it'd be great to talk with people who are interested. So the first thing that we're going to talk about today is quantum chemistry. Sort of how do you take quantum mechanics and then use it to simulate things that you might want to look at in chemistry and help accelerate an experimental process to synthesize a new material. And the way that we want to do that is we want to do that on the quantum computer. So we're going to talk about quantum algorithms that would allow for both near-term and then, in particular in this talk, long-term quantum computers in order to simulate things beyond what we can do with classical computing algorithms at this point. And so then we'll sort of conclude by bringing this full circle and talking about how maybe we can bring some ideas from the classical computer to the quantum computer and using that on some state-of-the-art quantum computing technologies to actually compute some things that we can't do right now. So if you're in physics, the last thing that you do in a quantum physics course is you talk about interactions between particles. And sometimes you don't even do that. But in principle, you should talk about how two electrons can interact with each other and what you can do. So, when you start up in a quantum physics course, you look at a non-interacting particle and, particles are fuzzy. So when they're moving back and forth in this box, you might think that the particle has some very clean trajectory that you can follow classically. But then on the quantum end, it no longer appears so distinct. It sort of smears out and gets very fuzzy due to the uncertainty principle. So these are the solutions of a Sturm-Liouville problem that corresponds to just a very simple example in quantum mechanics, which is a particle in a harmonic oscillator. And you can see that there are distinct energy levels that we get, and these correspond to the probability that we would sit in a particular location in the box. And so we have this really well-known equation that we can use to solve, which is called Schrodinger's equation. And Schrodinger's equation turns out to be so precise that in some cases it goes out to 20 digits, some unheard of accuracy in other fields, even quantum chemistry, although in principle it should apply there too. And if we take a look at what you do mostly in a quantum physics class, then you're mostly looking at things that don't have an interaction. So you have some kinetic energy operator, which allows the particles to move. And then you have some external potential, which constrains where the particles are allowed to be most probable or least probable. Well, we want to take one step beyond that. So there's a bridge here that we don't often teach in physics, but that you pick up right away in quantum chemistry. And that is, how do you actually use quantum physics to calculate something useful? So how do you actually do this in a way that would give you an answer that you might want to apply in a lab or something like this? And there's essentially two directions that you can think about working on this problem. You can work on the problem in terms of saying, how do I compute something on a computer? In other words, how do I actually set up the problem? How do I evaluate it? And then the other question is, what do I compute? So if you already have some computer software that would do this for you, then what am I actually going to get out of it? How can I actually tune my results so that I can get something useful for experimentalists and forward the scientific discussion? So in quantum chemistry, we have a fundamental advantage over my particle physics colleagues. We know what the Hamiltonian looks like. It's very simple. It's just one more step than what we already saw, which is to say that there's a kinetic energy operator, there's an external potential term, but then there's also an electron-electron interaction. So in particle physics, you're constantly wondering whether you're actually calculating the right field theory. In this particular case, we know it exactly. So we can really focus on the actual methods that we would use to solve it rather than how do we actually set up the Hamiltonian? Now, if you express it like you would in a normal quantum mechanics course, you have to use what's called first quantization. In other words, wave functions that have a particular property, and then find the eigensolution that satisfies the eigenvalue problem for the Hamiltonian. Now, there's also another way to phrase this, which is in terms of second quantization, which is instead of taking continuous fields and continuous wave functions and trying to solve for them, what you can do is you can designate basis functions or little spots in your quantum system, and you can define a Hamiltonian that allows electrons to hop between those spots in the system or to interact if they're sitting on different spots. So this is what the Hamiltonian, it's the same Hamiltonian just written in this different way. And you can think about the spots in the system being a Gaussian or being a Wannier function or a Muffington orbital or some local combination of atomic orbitals or really whatever you want to pick. The idea is that as you increase the number of basis functions, you'll approach the answer that you would get if you were using the full continuum Hamiltonian. So the natural question is, how hard is this? How much progress should we actually be expecting to make on this? And the answer is, depends on how optimistic you are, depends on how lucky you feel. So for my computer science colleagues, this is sort of where computer science can come in handy. The computational complexity of computing an average or the worst case scenario quantum many-body problem is called QMA hard. So that's quantum Merlin-Arthur hard. So it's one of the hardest problems in the computational complexity class. And it essentially means that we should not expect to find an efficient solution in general for quantum many-body problems. And that's true for both the classical computer or for the quantum computer. Both of those would have the same difficulty in finding them. Now, you might be looking at this and be saying, oh, well, if it's not easy, why should we do it? And the answer is that we can make better batteries for you. We can make better medicines. But even though this is a really hard problem to do, finding even just approximate answers for this can lead to big technological advances that can really, make a better cell phone for you if you want to think about it like that. So this is a paper that we'll sort of come back to later in terms of density functional theory, which is my next topic that I want to talk about. So back in 1964, there was this guy who's pictured here, Walter Kohn, and he came up with what is now called density functional theory. It essentially says that you can take the wave function from quantum mechanics and replace it with the one-body reduced local density matrix. And there's a formal proof for this. So it's called the Hohenberg and Kohn theorem. It says that you can replace the wave function with the density. And it provides a very compact representation for your quantum system. Instead of being expressed in 3 times the number of electrons in your system in terms of the number of coordinates, so that's an X, Y, and a Z component for every electron in your system, there's only 3. So it's a reduction on the order of the number of electrons. Now, this is provably equivalent to just regular quantum mechanics, but as things go, you need to introduce an approximation to actually use this. So in 1965, Kohn and Sham, which is the more popular version of density functional theory by far, said that you can actually make an approximation to a many-body expansion and then get something. But we'll talk about that in a second. Now, there's a whole bunch of other methods in quantum chemistry that aren't going to be particularly useful for this talk, but they're very useful in actual research. And those I'm just going to attribute to John Pople. So things like Hartree-Fock random phase approximation, coupled cluster methods. They're not all directly from John Pople. Hartree-Fock obviously is from Hartree and Fock. But these, there are other methods that you can use on the classical computer. The point is that all of them are approximate. All of them leave off Feynman diagrams in the expansion of the many-body term. So in the expansion of the many-body energy. So if we accept that we can make some approximation here, we can make the problem easier, but it's going to come at the cost that the eventual result is going to also be approximate. So when you simulate something and you make it in the lab, your battery might catch on fire, which isn't useful for us. So let's talk about some formal math, and there is some math in this talk. I'm sorry, I don't do anything practical, so instead of fun pictures, I have fun things to think about, which in this particular case is the one-body reduced density, which is given here. And I apologize, I should not have written integrating over R. So if you just leave off this term here, then you should get only one coordinate. So what I was saying earlier about having a number of electron terms and having 3 of them for every electron, the one-body reduced density matrix should only have 3 at the very end. So density functional is formulated in the broadest sense possible on a very large minimization problem. So if I find the one-body reduced density matrix that minimizes these 2 functionals, and by functional, what I mean is something that takes a function, like a density, and then maps it to a scalar quantity. And that just, in general, in mathematics, that's called a functional. So if I input a function here, I should get an energy here. And if I just knew what these 2 functionals look like, then I'd be able to solve just about any problem that I want to in terms of density functional theory. And it turns out that half of that is possible. So half of the functionals here, the external potential term, is known exactly. This is what the external potential functional looks like. Good news. Okay, well, what about the other one? F. I have no idea. F is so difficult that it causes all of the complexity of the problem to be wrapped up into it. And this, the only useful fact about this extra universal functional is that it doesn't depend on the external potential. So if I write down the form of this for one problem, it should be the same for every problem. And let me phrase that a little bit more exactly. This term should not have the external potential. So if I find a form for it, it should apply to any problem that I have. And I can just attach on a different external potential functional, and it will minimize to the correct ground state energy. Now, like I said, this is not exactly the way that we do quantum chemistry on the classical computer. We have a bunch of approximate functionals that we use that leave off different parts of the many-body energy expansion here. And the idea is that if I pick one of these approximate functionals, then I'll be able to compute the approximate physics or the approximate chemistry, and then use that to get an approximate answer that vaguely looks like what I get in an experiment. It would be really nice, though, if we could sort of ignore all of these approximations and just use the exact density functional theory. That would be the dream here. So let's turn now to quantum computing. And on quantum computing, we have sort of near-term demonstrations of what we can do with a quantum computer. And so there's a sort of a lot to pick apart from this example here. First of all, it's nearly 13 years old, so we have much better results. But I think the more recent results still tell essentially the same story. We've only come so far in 13 years. We'll go a little farther soon. We have here 3 planar molecules, which are not the most complicated things you can think to solve in quantum chemistry. You might think that you might want to solve a buckyball or a water molecule, which is slightly bent. And it turns out that we do have effective demonstrations on the quantum computer of water molecules. But the point is that you can't go to too many electrons and get something that is vaguely accurate. And you might look at these black dots, which are the evaluation on the quantum computer, and think, oh, we're actually doing pretty good. But if you look at the scale here, 1/1000th of a Hartree, 1/1000th of this distance here, so about this much, is the accuracy that you need in order to compare against experiment. That's how good experiments are. So when you see even a slight deviation of the black points from the exact curve, which is the dashed line, you might think, oh, well, that's actually, we can actually do better with that on a classical computer. And then there's some other points that you can take apart from this diagram. There's a basis set error, which means that your binding region isn't going to perfectly get all of the correlations in that region. And like I said earlier, all of these are planar molecules. So it's not exactly going, you shouldn't be inspired to think that this is going to compete with classical methods anytime soon. So let's talk about some constraints that the quantum computer has. First one is that it's noisy. So it's uncertain that you're not sure what state the qubits are going to be in. And until we have large-scale demonstrations of error correction, this is going to continue to be true. Now, there's also another problem, just algorithmically, that when you're writing a code on a classical computer, you can say A equals 2, and then you can say C equals A. So you can copy information around. Turns out that there's a very simple proof. I think it's about a page and a half in Nature a long time ago. So standards were lower, I suppose. But it says that there's no ability to take the wave function and then copy it onto a different set of qubits, so long as they're in an angled state. There is a serious advantage for quantum computing that should make us think that there's going to be algorithms that are going to allow us to do much better than the classical computer. And that is that there's less memory. So if I take a certain number of bits to represent an integer on the classical computer, I can represent it in some superposition of a qubit on the quantum computer. And this is going to cause an exponential compression of the memory in that case. The other thing that should be pointed out is that simple operations are harder. So, for example, addition has a very high gate count on the classical computer and on the quantum computer. And it's much more difficult to design an algorithm that would actually take advantage of the addition and then be able to pull that result off efficiently. So when I say that operations are often harder, you have to sort of rethink how you're going to do quantum chemistry on a quantum computer, because you want to avoid the explicit computation of some integral midway through an algorithm. You can do it as the expectation value of the wave function at the end, but you want to avoid a situation where you're doing too many operations on the classical computer versus the quantum computer, where they might not scale as well. Now, for my experimentally minded colleagues, I don't concentrate in this talk about how I would actually implement this onto a quantum computer. I risk to say that I don't care. I do care, just not in this talk. So we're just going to talk about sort of reversing the Copenhagen interpretation. We trust the laws of quantum mechanics so much that if we write down something that obeys von Neumann's postulates, we will assume that our experimental colleagues will be able to then go and implement. But so long as I don't make a math mistake somewhere, then I should feel pretty confident that these are algorithms that I can actually implement. So the first example of a quantum algorithm, I already know what question is going to come in the question and answer period, and I'm ready for it, is Grover's search algorithm. So Grover's search algorithm, there's a provable lower bound for how quickly you can search through a vector classically. So if I have a vector set up here, the first element is 3, the next one's G, the next one's 200, the next one's 12, and maybe there's a star symbol in the next bin. The question is, if I want to find one of these elements, how many bins do I have to search through on average in order to find it? And the answer is the number of bins. So order n is what we would say. Now, Grover was looking at some analogies between quantum algorithms and coupled harmonic oscillators. So if you're interested in sort of the classical intuition that led to this algorithm, I recommend looking at this article. But you can provably show that if you set up a search algorithm on a classical computer, that it takes less time to search for the element in the vector than on the classical computer. Now, this is somewhat misleading because this vector is exponentially sized, but the overall point is still there. Given two vectors, the quantum algorithm will beat the classical algorithm, provably so. And there's a few other notable algorithms. There's Shor's algorithm, which factors integers and basically can break the security on your cell phone. Then there's also the Deutsch-Jozsa algorithm, which has no practical application, but does have a provable quantum advantage. And the point is that if we come up with an algorithm that actually will do this for us, then we should be able to hopefully apply it onto really hard problems like quantum chemistry. So Grover's search vaguely looks like the following. You introduce an equal superposition over all states. So on our diagrams, we can draw our qubit states as lines. I'm going to refer to them as registers because it could be more than one qubit. And the idea is that if we apply this gate, which is listed here, which is called the Hadamard gate, then we'll generate an equal superposition of all possible states. And if you then apply a reflection operator in this space, you'll be able to tag the states that you want with a parity and be able to switch that back and forth. And then you'll be able to generate the correct state out of the entire superposition. Now, the question is, can you apply this on density functional theory? So I had a minimization principle that was used for this. Maybe there's a way that I could just apply this algorithm straight out of the box and then discover the universal density functional. Easy thing, hopefully, win a big prize and never have to touch physics again or something. But the question is, what is n? I already sort of gave this away, but it's an uninformed search over all the possible densities in the system, not even the ones that make physical sense. It's just all of the possible values that n can take. Now, if I apply my minimization principle over this, I'm searching over an exponentially sized database, which means that it's going to take an exponential amount of time in order to do this. So Grover search is not feasible here. We need to do something that is much better than Grover search in order to find this super efficient reduced version of quantum chemistry. So this line contains all of quantum chemistry in it, but we can't find it in a reasonable amount of time. So we need to come up with a better algorithm to do this. So let's take a look at what is sort of in the here and now. What kind of quantum algorithms can we apply in the near term? And the one that I would say is the most popular outside of QAOA. I always think it sounds like come sail away. So I never remember. Yeah, come sail away. So QAOA. But the idea is that there's the variational quantum eigensolver, which essentially evaluates expectation values of operators on the quantum computer. Now, once you evaluate those expectation values, you can go back to the classical computer and say, how did I set up my wave function in the first place? And I did it with a bunch of classical parameters theta here. And if I have some algorithm on the classical computer that would update those parameters theta, I can put it back onto the quantum computer, have it evaluate the expectation value, and then progressively search for better and better parameters here. Now, this isn't a perfect strategy. There's a lot of work being done on the classical computer, and you know about quantum chemistry, the evaluation of these expectation values are in a Gaussian basis can be done analytically, essentially. So you kind of wonder what we're actually getting here, but it is a demonstration on the quantum computer. The problem is that determining these classical parameters is harder than is super efficient. So this isn't an algorithm that we should expect is going to solve all of our problems, but it is a very good first step. The other thing is that it's very noisy on the near-term classical computer. So you're highly reliant on some sort of error mitigation strategy. So let's talk about some other algorithms that have been introduced through time. So the original motivation for looking at quantum chemistry on the quantum computer, an algorithm that said we might be able to do something useful here, was to take the time evolution operator and then decompose it with the Trotter-Suzuki decomposition. And just to remind you, if you've taken a quantum physics class and used the Baker-Campbell-Hausdorff transformation, then you can see that you can break up the Hamiltonian into subpieces, A and B, or maybe you have more, at the cost of making an error in this time evolution operator on the order of p squared. And so actually, this is the algorithm that got us the result earlier. And the question is, how long do I need this to run? So for my computer science colleagues, you can look at this and say, for a Hamiltonian phrase in the local basis set, in some sort of local basis set, that computationally this would only cost order n squared, the number of basis functions that I need. But the question is sort of how many of those n squared operations do I need to apply in order to obtain the final answer? So this was finally done in 2014 in this paper. And the answer was for a 36 electron molecule, it took months to run on small molecules. Now, there's nothing about this algorithm that you couldn't implement on the classical computer. There's no fundamental limitation here to just applying this on a classical computer. And the question is, when you show up to a quantum chemistry conference, why doesn't anyone use that particular strategy to solve for molecules? And the answer is this: it takes forever to do. We have much better things if we introduce a small approximation. The problem for my chemistry friends is that when you have things like conical intersections, you need to make sure that if you take too big of a time step, when you go from some non-interacting Hamiltonian to an interacting Hamiltonian, so the same basic construction as we use in quantum field theories or things like this, as you slowly tune in that interaction, you need to make sure that you don't jump into the next excited state. And what this means is that you need to keep T very, very low. So this is a problem. This is a major problem where we're proposing algorithms and then they're just not feasible to actually implement on the quantum computer. So the question is, what do we do? How do we save this and help the investors in the private sector get money? So this is my contribution to things. So this, I think, is sort of out of order from how we discovered this while I was in Sherbrooke. But the idea is to take an algorithm from the classical computer called a Lanczos algorithm. So a Lanczos algorithm takes any generic input, and I'm going to show the Hermitian version for this, so any generic Hermitian operator, and generates a tridiagonal representation of that operator. So these the terms in the tridiagonal Hamiltonian are the alpha coefficients and the beta coefficients. And if you run this Lanczos recursion algorithm, then in principle, you'll be able to generate the exact answer in a very small number of steps. So how do you actually do this? So if you're looking at this and you've only studied introductory quantum computing, you might say, aha, H almost looks like a unitary, except that I must apply everything on the quantum computer as a unitary. But the Hamiltonian can be decomposed into what's called a linear combination of unitaries. So this is a technique that has gotten much more popular over the last 7 or 8 years. It essentially came out of signal processing and allows us to apply generic operators onto the wave function. Finding what the linear combination of unitaries is here is not perfectly straightforward. If you want to go even simpler, you can think about the Hamiltonian being composed of independent unitary operators. And by unitary operators, I mean they're unitary up to a scaling factor. So if you just normalize out the scaling factor and just apply unitary pieces of the Hamiltonian independently, then you can think about applying this onto the wave function, and we'll forget about what the alpha and beta coefficients here are. The point is that you can map this problem onto a unitary and then apply that unitary in the quantum circuit. And this is all other people's work. I should cite Roland Soma and Kothari's PhD thesis from 2014, where they really explored how to do this. Now, the other question that you can ask is, okay, if I believe that I can actually write these operators in terms of unitaries, these types of gates that I need to apply on the quantum computer, then I also need to have some way to ensure that when I apply an operator onto a wave function, and the wave function is not an eigenvector of that operator, that I actually get the right product of those. And that can be handled with something that looks like Grover's search on the quantum computer, but it's called oblivious amplitude amplification here. It essentially generalizes what's called a repeat until success strategy to ensure that I apply the correct operator onto the wave function. So once I've guaranteed that the operator is applied correctly, once I've rewritten the Hamiltonian in terms of this linear combination of unitaries, everything that appears in this first line is fine to do. There's no algorithmic difficulty in doing that. There's no hidden oracle except discovering what the linear combination of unitaries are if you choose to do that. But I'm not sweeping anything under the rug here. Now, like I said earlier, it takes a couple of months to generate small molecules with real-time evolution. The question is, what do I do once I generate that wave function? Well, once I generate that wave function, I measure it. I don't even get the full expectation value. So I have to generate the wave function again, and then measure it again, and then keep doing this. So once you've spent a couple of months computing this, you need to redo that several times in order to get good statistics on the final expectation value. So while I was at Sherbrooke, it was mentioned last time by the speaker that David Poulin was a tour de force in quantum computing, and so he was my advisor for all of this. But he had come up with this way to avoid completely destroying the wave function. And so we're going to take a little bit of a detour into talking about how to do that, sort of round out how this algorithm works. And the idea is that we want to take minimal wave function preparations on the quantum computer just because that's fewer operations. So if we have some post-processing step that it itself is more efficient, then we should be able to perform this sampling trick and avoid recreating the wave function every time, which would cost a few operations to do. So the idea is that we want to do some sort of, there's a couple of different names in the literature. David would always call it quantum counting. So I just added state preserving quantum counting on because there's another algorithm called quantum counting, which is very different, more like Grover's search. But this is essentially going to count numbers of transitions between wave function states. It also goes by quantum Arthur Merlin sampling, and then also quantum amplitude estimation is another way to talk about it. And the essential, the key development that this really helped was, I think 2012, 2011, somewhere around there. But it was trying to put regular classical Monte Carlo onto the quantum computer. Okay, so let's take a little bit of a tangent to remind ourselves what Monte Carlo sampling is. So I'm not going to call it quantum Monte Carlo because that's already an algorithm. So I'm going to call it quantum Metropolis sampling. And the idea is that given a set of spins that are sitting here in a lattice, we want to flip a coin to determine a random number, determine some random spin in the system, and then we're going to flip a second random number for a second random number and determine whether we should flip that spin or not. So the idea is that it's flipped forwards and backwards. So the idea is that once we flip this spin, then we'll be able to figure out what the good thermodynamic quantities are of this lattice. So what David suggested on that paper, and one of his algorithmic contributions, in contrast to the quantum error correction contributions from last talk, is that you can essentially store the eigenvalue of some given wave function on some separate register. And you can apply some operator C here, so that when you then estimate the with quantum phase estimation, estimate the eigenvalue again, you could compare what you had before and what you had after. And if they match with a 0 on some comparator qubit, so you take these two and just compare with a series of C naught gates, whether you get 0 or 1. And then you can say, well, if I have the same wave function again, then that counts as one success. And if I get a failure, then I have to go back, and there's a way to undo this circuit so that I get back to the original wave function. We'll just take that on faith for a second. But the point is that there's a very simple formula to demonstrate what's going on in this circuit. If I take my original wave function describing my spins and apply a spin flip operator, and I wind up in the same wave function, then the number of times that it takes me to do that, divided by the total number of attempts, gives me the expectation value of this operator. And if I wind up over here, I claim that there's some way to come back to the original space. So this solves a major problem on the quantum computer for doing Monte Carlo sampling. If I need to flip that spin, I need to store two different spin configurations. And this is a real problem for me, because if I can't copy the wave function because of the no cloning theorem, then there's no way for me to actually perform the exact same algorithm on my classical computer as on the quantum computer. What this does is it allows me to store both of those in a superposition, and then to constantly try and select the one that actually has the correct wave function at the end that tells me whether I should flip the spin or not. And at the end, I can do some post-processing and then continue to do this and derive a square root speed up on Monte Carlo. So this is a general program that we can implement to generate the expectation value of any operator. There's no wave function that's destroyed completely here. It's reversible, so if I wind up in the bad sector, I can come back. And the idea is that if I can apply this in a variety of situations where I just want to get the expectation value off the quantum computer, I can save myself a bunch of wave function preparation techniques. Now, it turns out that Lanczos recursion is in the class of algorithms that allows this to happen. There's a lot of algorithms that would allow you to do this. But really, the reason to do Lanczos is because it would allow you to access quantities that you can't get very reliably on the classical computer. So, for example, the Green's function essentially describes the entire properties of the system. So if I want to generate the full interacting Green's function here, I can convert the problem into what's called a continued fraction at some given frequency omega. And if I generate my Lanczos coefficients alphas of 0 and beta and on down the chain, and take this single expectation value, which I now know how to do because of the previous algorithm, then I'm able to generate these expectation values, this expectation value, and I can complete the continued fraction out to any level that I want to do here. Now, there's a major advantage to doing this over the classical computer, in that the classical computer would have an accumulation of round-off errors as I go deeper and deeper into the levels of this continued fraction, which means that I'm never going to get Lanczos coefficients that are particularly accurate past a certain level, just because I only store out to 12 digits or so, and these accumulate very rapidly. So what this means is I can get this quantity that we have trouble computing on the classical computer much more easily on the quantum computer. So that algorithm, quantum Lanczos recursion, gives me a way to generate the ground state wave function and the fully interacting Green's function on the quantum computer. And I also extended this to excited states. So there's another variety of Lanczos recursion, which essentially takes the scalar coefficients beta and alpha and promotes them to matrices, which are given here. And this block Lanczos method only costs a polynomial amount more to compute the excitations. And the advantages to using this over just running regular Lanczos recursion is that it's a much more stable algorithm with respect to degeneracies in your system, and also to sort of several other properties that you might be interested in investigating. So this is just an extension to get the excited states. And what we can do is we can take our Lanczos algorithm and look at some near-term examples. So here I have a Heisenberg model, which has an XY term and then also a Z term on the end. And so if I just take the Heisenberg limit of this XXZ model, then I can run either two Lanczos operations, in other words, computing alpha twice, or computing alpha 4 times. And if I compare that with my tensor network solver, which is essentially equivalent to exact diagonalization, then I can see how adding an individual Z term would appear if I just run Lanczos with these very limited numbers of parameters. So what I'm doing here is I'm purposefully setting up a non-interacting Hamiltonian here, which just has the X and the Y terms in it. And then I add the first pair of terms, compute for the new ground state, and then I add the second pair of terms and then compute down. This is essentially doing that program that I talked about earlier, where I just want to add in Hermitian terms from the Hamiltonian one at a time. And now we can see how well Lanczos does. Well, it does go almost perfect. We're almost getting almost exactly the right ground state energy, at least on this very fine scale. And you can see that as you increase the number of Lanczos operations here, you get closer to the ground state. Now, if we were thinking about, quantum chemistry and quantum chemical accuracy, that's really only 1/1000th. So this algorithm is actually doing particularly well here, even by the standards of quantum chemistry. And it's so quickly convergent that if you ask the same question, but in a much more strongly interacting regime, where the JZ term is much, much larger than the XY term, then you might start off again with the non-interacting Hamiltonian, and then just apply 2 Lanczos steps and get down to the next term. So it's very rapidly converging in the number of Lanczos steps that you have. Now it messes up a little bit for just 2 down here, but if you increase it to 4, or if you take the interaction term and have it and then add it twice, then you can see that you're getting very, very good energetics here all the way throughout the chain, even though this is sort of easily perturbative to the regular non-interacting model. Now, on the quantum computer, it would be a little bit difficult to implement this, but since we're doing a classical simulator here, we have the advantage to say, what if I start with a random wave function? Maybe I know the Hamiltonian there, and I want to know what I'm doing. So if I start with just a random state, the initial energetics are particularly bad, and the original Hamiltonian has very little overlap with what comes after. But you can see that with just 2 Lanczos steps, they can immediately correct, come down here, even almost accuracy here. Now, if you're thinking from an experimental perspective, that you sort of have to get all of your gates to be perfectly accurate, the answer is that you can tolerate a little bit of error in your result. For every amount of error that you have along the x-axis of the diagram, because it's a tridiagonal Hamiltonian or a semi-tridiagonal Hamiltonian, so it doesn't matter how many excitations you're keeping in the model, there's a linear error. So every little bit you get more accurate on the quantum computer, you improve the results of the Lanczos algorithm by just as much. It's a linear relationship. So this is quite useful. This means that all of the effort that you put into it as perfectly as possible, or getting the error correction to be as accurate as possible, means that you're going to get something that is better and better for quantum chemistry. Now, to sort of bring this all home in the remaining 2 minutes that I have left, we didn't actually start looking at Lanczos recursion algorithms on the quantum computer. David pulled me into his, I'd like to say he kidnapped me into his office, and he tried to explain everything about quantum computing to me in 3 hours. And then he said, I had a paper where we had machine learned the density functional, or okay, fine. He was like, okay, we're going to do that, but on the quantum computer. And it sort of turns into this. I think this is one of his last papers, but the point is that you can pull density functional theory quantities off of the quantum computer using the tools that we've already talked about in the talk. And you can also derive things that you wouldn't expect to get exact on the classical computer, but can be derived exactly from the quantum computer. And we use this framework of minimal wave function preparation. So density functional theory from the quantum computer, let's go back to density functional theory and talk about what we actually need to compute. Just to remind you, the one-body reduced density matrix is a limit of a density matrix operator. So whatever orbitals you have here, if you take the limit of positive all time for the density matrix, then you should be able to get the one-body reduced density. And the coefficients can be measured from just this simple expectation value for some given state here. The citing this is on to make it simple. But the idea is that since we can measure this expectation value on the quantum computer, and we know what orbitals we put in to begin with, we can generate the density at the end. So what we want to do is we want to get the coefficients of the density matrix. If they're just expectation values, we can use the quantum counting trick that I alluded to earlier. And we can take the energy, which isn't represented on this slide, but was on a couple of slides ago, and the density, and that should be sufficient to characterize the full quantum system. Minus some phase information, which you can recover from some of the expressions on the following slide. So it's always V representable in what I'm going to talk about here, which means that there's always going to be a Kohn-Sham potential that I can find. And there's an algorithm in the literature that if I set up a cost function, this is the first Oracle query in the talk, how do you actually do this? But I allege that it's the quantum counting algorithm. Then you can variationally optimize for this Kohn-Sham potential, which is something that people use all the time on classical computers. And if you had the exact one, you could run very accurate, very efficient quantum computing algorithms all the time. Now, in order to do that, there's an algorithm called the quantum gradient algorithm, which very efficiently evaluates the gradient of any input function here. So if you use the quantum counting algorithm of the Oracle query here to generate the gradients in one Oracle query, that is fantastic, but I don't have time to go over it. So there's many varieties of density functional theory. So far, it turns out that everything we've been talking about so far is actually potential functional theory, kind of a subtle distinction there, which I don't have time to get into. But the idea is that if you set up your Hohenberg-Kohn theorem, not for the density, but now for the external potential, then you should be thinking that you want to find these functional derivatives that are here, but these can be given very easily from the quantum computer. So you can recover just about anything you need in density functional theory for exact density functional theory, and then solve your quantum chemistry problems exactly on the classical computer. There's also time-dependent density functional theory, but since I'm running out of time, we can skip that. You can also compute excitations, which is for the finite temperature density functional theory, which is closely related to ensemble density functional theory by using those ensemble density matrices. And there's a whole bunch more. You can go beyond the Born-Oppenheimer approximation. You can talk about relativistic density functional theory. You can quantum electrodynamics or spin orbit couplings for very large atoms and molecules. And so essentially, it also comes from just two algorithms on the quantum computer, which is quantum counting and quantum gradient algorithms. And I would argue that the setup of those wave functions could be done by my Lanczos algorithm from earlier. And you could do this for any type of density functional theory. So the entire zoo of approximations can just be overwritten by what we have here. And there's minimal measurements on the quantum computer, which means that you can use the quantum computer in the most efficient way possible that we know of. So in conclusion, we've come up with a couple of new algorithms for the quantum computer, largely related to density functional theory. These go beyond some of the previous attempts in the literature, which would have required a lot of wave function preparation and measurement. Along the way, sort of an accident of history, we discovered this Lanczos-based wave function preparation. And David did not get to see the end result of that paper, but I'm rather proud of it. And I owe the intuition on that to him. And but then we're also just using old algorithms that we all have known for at least 10 or 15 years. This one for 10 years, this one for 15. So this quantum counting algorithm lets us get the expectation value. This one lets us get the gradients on the quantum computer. We, as a bit of a surprise, we were able to find the continued fraction representation of the Green's function very efficiently from the Lanczos algorithm. We're able to get excitations. And the only thing that I'll sort of say in conclusion to this is, don't worry, this isn't going to replace your variational quantum eigensolver homework. This desperately needs error correction. So if you're working on that, then this will be a very useful thing for these algorithms. So I think I'm at my time. So I'd be happy to take any questions from online. Hopefully hopefully we had the mic turned on. And yeah, whatever questions you want to ask, I'll be happy to take them.